This course focuses at developing the concept of moment of inertia, and it also helps in deriving the moment of inertia of various objects without using complex integration. Normally the medical aspirants, they are not very comfortable with using integration, so I have derived the moment of inertia of various shapes and objects without using complex integration, and actually it is a logical derivation. So if you clearly understand that logical derivation, you will be able to derive moment of inertia of various shapes without tedious calculations. So first let us understand what is the meaning of moment of inertia. You already must be aware of the term inertia. Inertia is basically derived from the Newton's first law of motion or Galileo's law of inertia, wherein we say that every object in this universe has a natural tendency to remain in its state of rest or that of uniform motion, and we need to apply a force. And we have seen that mass is a measure of inertia. Greater is the mass, greater is the inertia. Now if we come to the rotational motion, when we want to set an object into rotational motion, we need to apply a torque. Torque is the turning effect of force. So when we apply torque to an object, it starts rotating, and we say that the object has an angular acceleration. Now for a given torque, if the moment of inertia of an object is higher, it will have lesser angular acceleration. So we say that every object has a tendency to oppose any change in its state of rest or that of uniform rotational motion, and the measure of this tendency is what we call as moment of inertia. As in translational motion, the acceleration is inversely proportional to mass of the object. Similarly, in rotational motion, the angular acceleration is inversely proportional to the moment of inertia of an object for a given torque. While the inertia of an object depends only on the mass of the object, the moment of inertia depends on the mass of the object as well as the distribution of the mass around the axis of rotation. So we will see that two objects, although they might be having same mass, may have different moment of inertia because of different distribution of mass in them. So first we will derive the moment of inertia in some standard cases, and then we will see how it is useful in other cases. Different systems that we will be having for moment of inertia, they can be broadly classified into two categories. One I call as the discrete particle system, and other I call as the continuous mass distribution. When I say discrete particle system, that means I have particles having masses, say m1, m2, m3 and so on, and these particles are located at certain fixed distances from the axis of rotation. For example, in the figure, m1 is at a distance r1, m2 is at a distance r2, and m3 is at a distance r3 from the axis of rotation. For such a system of particles, the moment of inertia is given by I is equal to m1 r1 square plus m2 r2 square plus m3 r3 square. So what I am going to do is I am multiplying the mass with square of the distance of that particle from the axis of rotation, and I add up all such terms. So this in short can be written as I is equal to summation mi ri square, where mi is the ith particle and ri is the distance of the ith particle from the axis of rotation, and we sum this product mr square for all the particles. That is shown by this notation I is equal to 1 to n. So it actually means m1 r1 square plus m2 r2 square plus m3 r3 square plus and so on till n. Now in case of a continuous mass distribution, we can write this as summation of dmr square. The basic idea for a continuous mass distribution is, in continuous mass distribution, we assume this mass distribution to be made up of a large number of very small particles, and these particles have masses dm. dm means infinitesimally small mass. So we are basically dividing the continuous mass distribution into small elementary particles, and suppose there is a particle of mass dm whose distance from the axis of rotation is r, then the moment of inertia for this particle will be dm r square. And if I sum, this sign of integration actually is an elongated s for summation. So the moment of inertia is summation of dm r square. It is similar to this notation. The only difference is in place of writing mi ri square, I am writing it as dm r square. So these are the two basic formula for moment of inertia, and we will be using these two formula to evaluate the moment of inertia in different cases. From these two formula, it is very clear that the moment of inertia depends on mass as well as the distance of that mass from axis of rotation. That is why I suggested that moment of inertia depends on distribution of mass. Keeping the mass same, if we double the distance of that particle from the axis of rotation, then moment of inertia will become 4 times, because Ri, if I double it, Ri square will become 4 times. So this is the logical thing that I am going to use in the later problems to come. So let us start with some simple cases. First, I will talk about a standard case of moment of inertia for a discrete particle system. I will use that formula in a special case, and I will illustrate how to use this formula. Suppose we have a set of two particles with masses m1 and m2, and they are separated by a distance r. We have to find the moment of inertia about an axis through. Whenever we are talking about moment of inertia, we must clearly define the axis. Only then we will be able to find the moment of inertia. So we want to find the moment of inertia about an axis through first part m1 and perpendicular to the line joining them. So we'll have to find the moment of inertia about m1 and perpendicular to the line joining them. So this is the axis of rotation. In second case, it is moment of inertia about m2 and perpendicular to the line joining them. That means I will be calculating the moment of inertia about this axis. Similarly, third part, moment of inertia perpendicular to the line joining, that means about this. Then about the center of mass perpendicular to line joining them. Center of mass may not be the midpoint, somewhere here, and I will have an axis like this, and I will calculate the moment of inertia. Let us take them one by one. First case. In first case, we have to find the moment of inertia about this axis. So this is the axis, and now I have to calculate the moment of inertia. So I will multiply m1 into perpendicular distance, which is 0, because m1 itself lies on the axis of rotation only. So m1 into 0 square plus m2 into the perpendicular distance of m2 from this axis is r. So m2 into r square. So answer to the first part is m2 r square. Similarly, let's talk about the second part. In the second part, I have to calculate moment of inertia about this axis. This axis, for this axis, it will be m1 into r square, because m1 is at a distance r, whereas m2 is at a distance 0. So it will be m2 into 0 square plus m1 into r square. So the answer is m1 r square. Now the third part. Third part is the axis through the midpoint. Midpoint means r by 2 from m1 and r by 2 from m2. So it is simply m1 into r by 2 square plus m2 into r by 2 square. That is m1 r square by 4 plus m2 r square by 4, and that can be written as m1 plus m2 r square by 4. I have been suggesting this continuously, and I again suggest that while I am illustrating these solved examples, it is strongly recommended for all the students that they solve these questions by themselves in their notebook, because only then they will be able to develop the understanding as well as the skills on the problems. Now the fourth part, which is about an axis through center of mass and perpendicular to the line joining them. So this is m1, this is m2. Let us suppose this is the center of mass C. I have to find the axis moment of inertia about this axis. Suppose the center of mass is at a distance r1 from m1 and r2 from m2. Now if C be the center of mass, then m1 r1 is equal to m2 r2. This result has been dealt with in the topic of center of mass. So for that matter, you need to go through the topic center of mass. Over there, this result has been derived. m1 r1 is equal to m2 r2. Also from the diagram, you can see r1 plus r2 itself is equal to r. So I can take r2 as r minus r1 or r1 as r minus r2, and I put that value in this equation to obtain this. I get m1 into, I have replaced r1 by r minus r2 is equal to m2 r2. Now in this equation I have solved for r2, which is r2 is equal to m1 r by m1 plus m2. So I have calculated r2. Now using this m1 r1 is equal to m2 r2, I will also evaluate the value of r1. I will put the value of r2 over here to obtain r1 as m2 r by m1 plus m2. So I know r1 and r2, and the basic formula for I is m1 r1 square plus m2 r2 square. So I put r1 as this m2 r by m1 plus m2 and r2 as m1 r by m1 plus m2. From this whole equation I can take out m1, m2 common, and I can also take m1 plus m2 whole square common. I can take r square common. In this expression, if I take that common, it will be left with m2, and similarly from this expression it will be left with m1. So once I take this common, it will be m1 plus m2 left in the numerator. There is m1 plus m2 square in the denominator as well, so we will cancel 1, and therefore I get I as m1 m2 by m1 plus m2 into r square. Generally this is written in short as I is equal to mu r square, where mu is m1 m2 by m1 plus m2. So that is just an example to understand how to use the formula for a discrete particle system. Now I'll give you a conceptual problem. This conceptual problem is based on the moment of inertia of a continuous mass distribution, and the answer can be calculated without knowing the actual formula. Let the moment of inertia of a thin bar about an axis through one end and perpendicular to its length be I naught. What will be the moment of inertia of another bar of same material but double the length about similar axis? So I have a bar and the moment of inertia about one axis is given to be I naught. We are asking the moment of inertia of another bar having double the length. So this is a problem based on scaling. We can solve this problem without actually knowing the formula. You must understand that moment of inertia is summation of dm r square. So it will depend on mass and it will also depend on the square of the length. So I can say that the moment of inertia of the bar must be somehow proportional to m into L square. So I say I naught is equal to cml square. I don't know the value of c, but I don't actually need to know it. Now suppose I naught is cml square, and I have a second bar of same material but double length. If we have same material and the length is doubled, then the mass is also double. Then the moment of inertia of that bar will be c. I replace m by 2m and I replace L by 2L. So it will be 2m into 2L square, and that will be 8 times cml square. So the moment of inertia will become 8 times. So keeping the material same, if we double the geometrical dimension of a thin bar, then mass will also double and therefore moment of inertia will become 8 times. If I am talking about a plate and I double the geometrical dimensions, length and breadth both, area will become 4 times. Moment of inertia will change in proportion to that also. So we will discuss about that in case of plates. So in this lecture I have given you the basic idea about moment of inertia, how to calculate the moment of inertia of discrete particle system, and I gave you an example based on scaling. In the lectures to come, we will calculate the moment of inertia of different shapes, and you will see how I calculate the moment of inertia without using typical integration. Hello students, welcome back. This is the second lecture on the course moment of inertia, and in this lecture we will be discussing a theorem. Basically we will be discussing 2 theorems on moment of inertia, and we will see how these theorems are useful to calculate the moment of inertia for different objects. Earlier we have discussed about a basic formula for moment of inertia for a continuous particle system, continuous mass distribution and discrete particle system. Now we understand 2 basic theorems, and then we will learn to apply these theorems to evaluate moment of inertia in different cases. So let us start with it. First of all, I will talk about the theorem of perpendicular axis. This theorem of perpendicular axis is applicable for a 2-dimensional object. that is a laminar body, means a planar body. For example, a ring, disc, triangular plate, square plate, thin bar, etc. It cannot be applied to a three-dimensional body like a cylinder or sphere or something like that, or a box. So you have to be very careful. Theorem of perpendicular axis is applicable for a 2D object. Suppose this is an object. I am showing this is an object. So this is an object. As you can see, it has no thickness. So it is a two-dimensional object. Let there be two axes, x and y axis in the plane. This is x axis and this is y axis. These x axis and y axis, they lie in the plane of the object, and there is a third axis which is the z axis, which is perpendicular to the plane of the object. Then the theorem of perpendicular axis states that the moment of inertia about z axis is going to be equal to the sum of moment of inertia about x axis and y axis. While using this theorem, you have to be careful. X and y lie in the plane and z is perpendicular. Normally what we do is, while solving the problems, we forget this, and if we see any two perpendicular axes, we evaluate the moment of inertia about third axis by adding them. That means you can do by mistake add the moment of inertia about y and z, and you can obtain the moment of inertia about x. That is wrong. You have to be careful. The two axes about which the moment of inertia we are adding, they lie in the plane of the object, and the third axis is perpendicular to the plane of the object. Now the moment of inertia about z is equal to the moment of inertia about x axis and y axis. Here is a simple proof for it. Suppose this body is made up of a large number of particles, and I consider one such particle dm, and suppose this dm has a perpendicular distance x from the y axis and perpendicular distance y from the x axis. That is how we represent the coordinate. X comma y is the position coordinate of this particle. Then if I calculate the moment of inertia of this object about x axis, it will be dm into square of the perpendicular distance from x axis, which is y. So it is summation of dm y square. Similarly, the moment of inertia about y axis, if I calculate the moment of inertia about y axis, it will be dm into square of perpendicular distance, that is x. So it will be summation of dm x square. And if I have to calculate the moment of inertia about z axis, I need to know the perpendicular distance from z axis, which will be in this diagram this distance. This is going to be the distance, perpendicular distance from z. Now if this is x, then this distance is also x. So this will be x, this will be y. So by Pythagoras theorem, this distance will be square root of x square plus y square. So r will be under root of x square plus y square, where r is the perpendicular distance from z axis. Then moment of inertia about z axis is integration of dm into r square, that is integration dm into x square plus y square. So clearly this can be written as integration dm x square plus integration dm y square, and integration dm x square is the moment of inertia about y axis, and integration dm y square is the moment of inertia about x axis. So I can write simply Iz as Ix plus Iy. So that is quite a simple proof. So Iz will be Ix plus Iy. I am again warning you, be careful. X and y must be in the plane and z must be perpendicular to it. So that is the theorem of perpendicular axis. Now we have the second theorem, which is known as the theorem of parallel axis. This theorem of parallel axis is applicable for any shape and size. You see, I have drawn a general shape, whereas in the previous case it was only a two-dimensional object. This is applicable to any three-dimensional object as well. So what is the theorem? Let ICM be the moment of inertia about an axis through center of mass. Suppose this is the center of mass and this is through center of mass and in any specific direction. Now suppose I have another axis which is a parallel to the previous axis through center of mass, and the perpendicular distance between them is d. Let I parallel be the moment of inertia about an axis parallel to ICM and at a distance d from it. The distance between these two axes is d. Then parallel axis theorem states that I parallel is equal to ICM plus md square, where m is the mass of the object. So if you know the moment of inertia about an axis through center of mass, you can find the moment of inertia about any axis which is a parallel to the axis through center of mass and displaced from it by a distance d. Then I parallel can be calculated as ICM plus MD square. You have to learn this statement carefully. It has to be ICM plus MD square. I'll tell you a common mistake that happens while solving the problem. As a matter of chance, you see two parallel axes and moment of inertia about one of the axis is given to you, and you have to find the moment of inertia about another axis. So without checking whether it is through center of mass or not, you tend to apply this formula that okay, I know this I1 and I want to find I2. I will write I2 as I1 plus MD square, which is going to be wrong. Be careful, it has to be ICM plus MD square, where M is the mass. So let us study the proof of this. To prove this, I assume that the coordinates of center of mass is 0, 0, 0. Suppose the center of mass axis is the z axis, and suppose this is the x-axis, this is the y-axis, and this other axis lies at a distance d. So for a simplicity sake, I have taken this point as d, 0 on x-axis. So this is the other axis. So if I have the center of mass as the z-axis, then for any particle whose mass is mi and whose position coordinates are xi, yi, zi, then the distance of this from z-axis can be calculated by looking at this figure. See, this is z-axis. On z-axis, x and y both are 0. This is mi, ith particle. Its position coordinates are xi, yi, zi. If I drop a perpendicular from this to z-axis, at this point, x and y both will be 0. Z will be the same zi. So this is xi, yi, zi, and this is 0, 0, z. If I calculate the distance between two using distance formula, it will be square root of xi minus 0 square plus yi minus 0 square plus zi minus zi square. So it will be square root of xi square plus y square. So the moment of inertia about center of mass will be summation of mi into this distance square, which will be xi square plus y square. So the moment of inertia about center of mass will be summation mi into xi square plus yi square. Now this is the other axis, which is a parallel to center of mass axis at a distance d. So this passes through d, 0, 0. That means at this entire axis, x will be d. So if I drop a perpendicular from I to this point will have coordinates now d, 0, zi. And if I calculate the distance of xi, yi, zi from d, 0, zi, it will be xi minus d whole square, yi minus 0 whole square plus zi minus zi whole square. So it will be mi into xi minus d whole square plus yi square. So I parallel will be summation of this. Now I open up this. I parallel will be summation of mi into xi minus d whole square plus summation mi into yi square. Now this I can expand this using a minus b whole square, which is a square plus b square minus 2ab. So I get summation mi into xi square plus summation mi into d square minus 2 times of mi into xi into d. So minus 2 times summation mi xi into d plus obviously this last term summation mi yi square. Now I parallel is equal to this summation mi xi square plus summation mi yi square, that is ICM. So I replace these two by ICM plus I am left with summation mi into d square minus 2 times summation mi xi into d. Now this summation mi d square, d is common, so I can write d outside. It is summation mi, which is total mass. So summation mi is total mass. Further, this summation mi xi, we know that summation mi xi divided by total mass is xcm, and in this case xcm is 0. So xcm is 0, that means summation mi xi is 0. So this term becomes 0, and in this term we get capital M. So we get I parallel is equal to ICM plus MD square. So we have I parallel is equal to ICM plus MD square. So these are the two basic theorems. One is the perpendicular axis theorem, other is the parallel axis theorem. Now we will be using these two theorems in different cases. So I will illustrate one example based on this. Just a simple example. Let I naught be the moment of inertia of a uniform ring about an axis through its center and perpendicular to its plane. There is a uniform ring. I naught is the moment of inertia about an axis through its center and perpendicular to its plane. That means this axis. So about this axis, the moment of inertia is I naught. Let I be the moment of inertia about a diameter. We have to find the ratio I by I naught. About a diameter means suppose this is a diameter and the moment of inertia about that is I. We have to find the ratio I by I naught. Now since the ring is uniform, the moment of inertia about any diameter is same. That means I can choose the diameter like this, or I may choose the diameter like this. So if I choose this as the diameter and this as the diameter, they two are perpendicular to each other and they lie in the plane of the ring. Now by perpendicular axis theorem, I can write Ix plus Iy is equal to Iz. So I plus I is equal to I naught. So I get 2I is equal to I naught. From this I will get I by I naught is equal to 1 by 2. So that is a simple example to use the perpendicular axis theorem. Now you have another interesting example. Without using integration, find the moment of inertia of a uniform thin bar about an axis perpendicular to the rod passing through one end. I have a bar of mass m, say length L. I am supposed to find the moment of inertia about this axis. And I don't want to use integration. Now we know that moment of inertia is going to be proportional to mass, of course, and it will be proportional to square of the distances. So I know that moment of inertia will be somehow of the form I is equal to CML square. C I want to find out. Now suppose I have I dash as the moment of inertia about an axis through midpoint of the bar perpendicular to its plane. Obviously this will be through center of mass. So I can write I, the moment of inertia about this axis, as ICM, which is I dash I have written, plus m into d square. D is the perpendicular distance between them. So I can write I as I dash plus m into L by 2 square. Now let us have a look at I dash. I dash is the moment of inertia of this bar about this axis. This entire bar can be thought of to be made up of two bars, half and half, m by 2, length L by 2, and this is also m by 2 and length L by 2. So this I dash is basically I dash is moment of inertia of this plus moment of inertia of this about this axis, say I1 and I2. So I can write I dash as I1 plus I2. Now since I is a CML square, so I2 and I1 obviously they will be equal. They are for a rod having mass m by 2 and length L by 2. So they must be of this form. So I1 and I2 will be CML square by 8. That means for the complete bar, if moment of inertia is CML square, for half of the bar it will be CML square by 8. Now as I said earlier, by parallel axis theorem, I dash is I plus ML by 2, ML square by 4. I replace I dash by I1 plus I2, and I1 plus I2 is CML square by 8 plus CML square by 8. I was supposed to calculate, which is CML square. So I is CML square, I dash is I1 plus I2. So I put this as CML square by 8 and I solve this to obtain the value of C, which is 1 by 3. So I get answer as ML square by 3. Hello students, welcome back. This is the third lecture on the course Moment of Inertia. In the first and second lecture, we have developed the basic concepts of moment of inertia. We read the formula for moment of inertia for discrete particle system for a continuous mass distribution. Then in the second lecture, we dealt with theorems on moment of inertia, particularly the parallel axis theorem and the perpendicular axis theorem. And we saw some interesting application, specifically the one in which we derived the moment of inertia of a thin bar about an axis perpendicular to its length and passing through one end, which we calculated as ml square by 3, and I showed how to derive that result without using integration at all. Now I will be using that base formula, moment of inertia ml square by 3, and using that simple base formula I is equal to ml square by 3, I will show you how to calculate the moment of inertia of a bar, moment of inertia of a plate, and moment of inertia of a box. So let us start with it. So I start with this information, that the moment of inertia of a thin bar, this is a thin bar, and the axis which is perpendicular to its length and passing through one end, the moment of inertia is ml square by 3. Right, so this is the result that I am going to use, and I will use this to evaluate moment of inertia for a bar, for a plate, for a box about a different axis. Let us see how. First I will talk about a rectangular plate. So a rectangular plate, mass m, length L, and breadth B. So this is a rectangular plate. This rectangular plate has a mass m, the length of the plate is L, and the breadth of the plate is B. And I will calculate the moment of inertia about an axis which is lying along the edge, and this edge is basically the breadth of length B. So I will calculate the moment of inertia about this axis. So this entire plate can be thought of to be made up of a large number of thin bars. So I have divided this into a large number of thin bars, and suppose this is one of such bars. This is what I call as a differential element of mass dm. So this is a thin bar of mass dm and length L. Now the moment of inertia of this thin bar of mass dm and length L about this axis will be dm into L square by 3. As seen in this result, the moment of inertia is ml square by 3. So the moment of inertia of this differential element about this axis will be dm into L square by 3. So the moment of inertia of the entire plate will be equal to the sum of moment of inertia of all these bars. Therefore it is summation of integration of individual moment of inertia, which is dm L square by 3. Now for all these bars the length is same, so L square by 3 can be taken as common out of the summation, and I will be left with summation of dm, which is obviously the total mass. So the moment of inertia is ml square by 3. So the moment of inertia of this bar about this axis is ml square by 3, and if I have a plate in place of this bar and this length is L, the moment of inertia is again ml square by 3. So what I want to convey is that the moment of inertia of this bar about this axis is ml square by 3. So what we observe is that the moment of inertia about this axis does not depend on this geometrical dimension, it only depends on this geometrical dimension. So moment of inertia will be obviously dependent on the perpendicular distance. So for this shape, the moment of inertia is dependent on this geometrical dimension, it is not dependent on this geometrical dimension. So I'll give you an example. Suppose I have a bar like this and I have this axis, and this bar makes an angle theta with this axis, and I want to find the moment of inertia of the bar about this axis. So this length L, I resolve it in two components. This is L cos theta and this is L sin theta. If I calculate the moment of inertia about this axis, it will not depend on L cos theta, it will depend on L sin theta, and the moment of inertia will be m into L sin theta whole square by 3. ml square by 3 is in this case, and in this case we have replaced L by L sin theta. So it is m by 3 L square sin square theta. Similarly, the moment of inertia about this axis. For this axis, the perpendicular distance is L cos theta. So for this axis, the moment of inertia will be m by 3 L square cos square theta. So with the help of these examples, I wanted to inform you that the moment of inertia will not depend on the geometrical dimension parallel to the axis. It will depend on the geometrical dimension perpendicular to the axis. So the moment of inertia will not depend on the dimension parallel to axis. So if I have a plate like this of length L, breadth B, and I want to evaluate the moment of inertia about this, it will be ml square by 3. Similarly, if I have a plate like this, uniform plate, I want to find the MOI, moment of inertia, about this axis. So it will not depend on L, it will depend on B, and the answer will be MB square by 3. In this case, it is the perpendicular distance is L, so ML square by 3. In this case, perpendicular distance is B, so it is MB square by 3. Now, by parallel axis theorem, we can also show that the moment of inertia about this axis is ml square by 12, which I have shown in the first diagram itself. For the thin bar, the moment of inertia about this is ml square by 12. I am giving the proof here. Now, this is the moment of inertia ml square by 3 for this length L. We have already derived this. Now, this is an axis through center of mass, and these two are parallel to each other. Then by parallel axis theorem, we have I parallel is equal to ICM plus MD square. Now ICM we want to find out. I parallel is this axis which is parallel to the axis through center of mass. So about this, the moment of inertia is ml square by 3. ICM is this plus m into d. D is the perpendicular distance between them, which in this case is L by 2. So this is m into L by 2 square. So this is ml square by 3 is equal to ICM plus ml square by 4. I take ml square by 4 to the left hand side. I will get ml square by 3 minus ml square by 4, which on solving gives me ICM as ml square by 12. So the moment of inertia about this axis now comes out to be ml square by 12. Let us extend it further. So now we know that for this plate, the moment of inertia about this axis will depend on L, and it will be ml square by 3. And the moment of inertia about this will also depend on L, and it will be ml square by 12. Now if you focus on this axis, the moment of inertia about this axis, the perpendicular distance is B, so it is mb square by 3. Similarly for this axis, it is the perpendicular distance is B, so this is mb square by 12. So have a careful look at this. This is ml square by 3, this is ml square by 12. If I take this as the axis, it is this dimension which is involved, and answer is mb square by 3, and for this axis it is mb square by 12. Now we will apply the perpendicular axis theorem to this plate. This is the plate. If I calculate suppose this plate has length L and breadth B. If I choose this as the axis, moment of inertia will be mb square by 3. The perpendicular length is B. Similarly for this, it is mb square by 12. Now for this axis, it is ml square by 3, the perpendicular distance L, and for this axis, it is ml square by 12. Now if I take an axis which is passing through center and perpendicular to the plane, this axis. Now these two axes lie in the plane, and this is the z axis perpendicular to them. So by perpendicular axis theorem, Iz will be Ix plus Iy. So this moment of inertia I1 can be written as ml square by 12 plus mb square by 12. ml square by 12 plus mb square by 12. Similarly, this axis is perpendicular to these two. About this, the moment of inertia will be ml square by 3 plus mb square by 3. So moment of inertia for rectangular plate about an axis through center and perpendicular to its plane will be ml square by 12 plus mb square by 12, and for an axis through its corner and perpendicular to the plane of the plate, it will be ml square by 3 plus mb square by 3. Now we know the results for a rectangular plate. We can extend these results to a box. Suppose I have a box of, say, uniform box cube of cuboid of length L, breadth B, and height h. As I discussed, I must not depend on the moment of the geometrical dimension parallel to this. Suppose I choose this as axis. If I choose this as an axis, then the moment of inertia will not depend on L. If I choose this as an axis, then the moment of inertia will not depend on B. And similarly, if I choose this as the axis, the moment of inertia will not depend on H. right? So for this case, the moment of inertia I1 will not depend on the geometrical dimension L. So it will be mb square by 3 plus mh square by 3. Have a look at this result. In this plate, the moment of inertia about this axis is m L square by 3 plus mb square by 3. So if we extend this plate parallel to this to make it a box, then the moment of inertia expression will remain the same. So if I talk about this axis, the moment of inertia will be mb square by 3 plus mh square by 3. So you talk about this. Suppose this is L, B and H. I talked the moment of inertia about this. It will not depend on H. So I look at this rectangular plate LB, and the moment of inertia about this axis is ml square by 3 plus mb square by 3 as derived earlier. So for this box also, about this axis, the moment of inertia will be ml square by 3 plus mb square by 3. Similarly, the moment of inertia of this box about this axis will be same as the moment of inertia of a rectangular plate about an axis through center and perpendicular to its plane, which we evaluated as m into L square plus b square by 12. So suppose we have a box like this, and I want to find the moment of inertia about this axis. It will not depend on H. So answer will be m into L square plus b square by 12. If we have this axis, this is parallel to L, so moment of inertia will not depend on L. It will be m into b square plus h square by 12. Similarly, if we have this axis, then the moment of inertia will be m into L square plus h square by 12. So in this example, I started with the basic formula ml square by 3 for a rod, and I explained you how you can extend it for a rectangular plate and a box. In this lecture, we will be talking about the moment of inertia of a square plate, cube, triangular plate, etc. In the previous lectures, we have talked about the basic concepts of moment of inertia. We learned about various theorems on the moment of inertia, and we also calculated the moment of inertia of a thin bar about some axis, and then we extended that concept to rectangular plates. Now we will be talking about square plates, then we will extend that to cube as well as triangular plates. So let's start with this. Now we already know that for a rectangular sheet, the moment of inertia can be calculated as shown in this diagram. I have a rectangular sheet. This length is L, this length is B. The moment of inertia about this axis will depend on L. It will be ml square by 3. The moment of inertia about this axis will be ml square by 12. Similarly, for this axis, the moment of inertia will depend on B. It will be mb square by 12. The moment of inertia about this axis will be mb square by 3. This we have already calculated. Now, if I talk about a square plate, then in case of a square plate, this L and B become equal, and if this L and B become equal, I write both of them as L. Now the moment of inertia about this axis is ml square by 12, as already seen. The moment of inertia at this axis is also ml square by 12. Now we can apply perpendicular axis theorem. These two axes may be taken as x-axis and y-axis lying in the plane of the object. This is the axis perpendicular to the plane of the object, may be taken as z-axis. Now by perpendicular axis theorem, Iz is Ix plus Iy. So Iz can be written as ml square by 12 plus ml square by 12. So it is ml square by 6. So the moment of inertia of a square plate about an axis through its center perpendicular to its plane is ml square by 6. Let us extend this result further. Now we'll extend this to a cube. For a square plate, the moment of inertia about this axis is ml square by 6. Now as we have discussed earlier, that moment of inertia will not depend on the dimension to the axis. So the moment of inertia will not depend on this dimension. So if I extend this dimension, the result will remain same. So I extend this square plate to make a cube of length L, L and L, all the edges are L. Still the moment of inertia about this axis will be ml square by 6. So for a cube, moment of inertia about an axis through the center of one of the face and perpendicular to that face will be ml square by 6. If I know this, I can also find the moment of inertia of a cube about an edge. If this moment of inertia is ml square by 6, I can find this using parallel axis theorem. This is the moment of inertia about an axis through center of mass. We can find this distance. This is L, this is L, so this becomes L root 2. Half of this will be L root 2 by 2, which is L by root 2. So this length is L by root 2. Now if this is ml square by 6, I can find this using parallel axis theorem, which says that I parallel is ICM plus MD square. So ICM here is ml square by 6, D here is L by root 2. So this is ICM plus MD square, that is ml square by 6 plus into M into L by root 2 whole square. L by root 2 whole square becomes ml square by 2. So this is ml square plus by 6 plus ml square by 2. We take the LCM, we get ml square plus 3 ml square, that is 4 by 6 ml square or 2 by 3 ml square. So the moment of inertia of a cube about this axis is ml square by 6, and about this it is 2 ml square by 3. So that is about a cube. Now we talk about a very important result for a square plate. Suppose we are given a square plate. This is a square plate and we want to find the moment of inertia about an axis through its center lying in the plane of the plate, but it makes an angle theta with this. About this axis we already know the moment of inertia. Let us call this as x-axis. Then the moment of inertia about this axis we already know ml square by 12. Moment of inertia about this axis we already know ml square by 12. If I take a third axis which is perpendicular to the plane of the plate, let us call it as I naught. Then by perpendicular axis theorem, I naught will be Ix plus Iy, ml square by 12 plus ml square by 12, that is ml square by 6. Now suppose in this plate I have an axis which passes through the center, but it is making angle theta with this line, suppose. To find this, what I do is I choose, this is the square plate, this is the moment of inertia which I want to find. I can draw a similar axis over here. This is x-axis, this is y-axis. For a square plate, x and y are identical to each other. So if I have this axis making angle theta with x-axis, I choose another axis which also makes angle theta with y-axis. By symmetry of this plate, we can easily say that the moment of inertia about this will be same as the moment of inertia about this, and these two are going to be perpendicular to each other. So if these two are going to be perpendicular to each other, then Ix plus Iy can be written as Iz. That means I can write I naught, which is the moment of inertia about the axis perpendicular to the plane, as I plus I. Therefore I is I naught by 2. I naught we have already calculated ml square by 6, so the answer is ml square by 12. Now in this part, basically what I want to tell you is, for a square plate, if you have any axis through its center lying in the plane of the plate, the moment of inertia is going to be ml square by 12. So that is a useful result. This is a very popular question usually asked in various examinations. Now we'll apply these concepts to find the moment of inertia of a triangular plate. So I'll be talking about a triangular plate. I will start with a simple case. Suppose I have a right angled plate. So I take a right angled plate. Suppose the mass of the plate is m, height is h, base is b, and now I want to find the moment of inertia of this plate about this axis, an axis that coincides with this edge. Now to find the moment of inertia about this edge, what I do is I take another similar plate and place it over here like this. The mass of the original plate that we had was m. We take another plate, similar plate of mass m, rectangle plate. I place it over here so that I obtain a rectangle. And suppose the moment of inertia of this whole rectangle about this edge is I. Now this I is basically contribution of this plate, which is I naught, and the contribution of this plate, and the contribution of this plate is suppose I dash. So the required moment of inertia of this entire sheet will be I naught plus I dash. There is a slight typing mistake over here. I have written slightly wrong. I wanted to find this I. So this is I naught actually. The moment of inertia of this complete plate about this axis is I naught, and it is the moment of inertia of this plate, that is I plus I dash. So you read this as I naught and this as I. So I have I naught is equal to I plus I dash. I is something we want to find. Now first I will find I dash. To find I dash, I take this plate, the other plate which I placed. For this plate, if I choose this as the axis, the moment of inertia is I, which we want to find. And this we have assumed as I dash. I will relate I with I dash. For that I will use parallel axis theorem. For this plate, the center of mass is, suppose here, the center of mass is at a distance, at a height h by 3 from the base. So if this is height h, then this is h by 3, and obviously this will be 2h by 3. And suppose there is an axis through center of mass parallel to this edge. So this ICM and I can be related by parallel axis theorem as I parallel is equal to ICM plus m into h by 3 whole square. So I get I is equal to ICM plus mh square by 9. Similarly, I can relate I dash and ICM by parallel axis theorem. I dash is ICM plus m into 2h by 3 whole square, that is ICM plus 4mh square by 9. Now from these two equations I can relate I dash and I subtract them, I dash minus I. When I subtract these two equations, ICM and ICM cancel out. So I will be left with 4mh square by 9 minus mh square by 9, which is 3mh square by 9 or mh square by 3. So I dash and I now we got related. I will put the value of I dash in this equation. So for this complete plate, the moment of inertia was assumed to be I naught, which is I plus I dash. Here I have corrected, see, I naught is I plus I dash. Now for this entire rectangular sheet, the mass is 2m, and we know that for a rectangular sheet, the moment of inertia is mass, that is 2m, into h square by 3. Like for a rod also we calculated ml square by 3. So for this axis, for this rectangular plate, it is mass into h square by 3. So I naught is 2mh square by 3. I we wanted to calculate. I dash we have evaluated in the previous page as I plus mh square by 3. So I replace I dash as I plus mh square by 3. I take this mh square by 3 to the left hand side. So 2mh square by 3 minus mh square by 3 is equal to 2i. That is mh square by 3 is equal to 2i, and that gives you I is equal to mh square by 6. So for any right angled plate, the moment of inertia about this edge will be mh square by 6, where h is the height. Now we'll see that this can be extended to other plates. I will prove that for any plate about an edge, the moment of inertia is mh square by 6. Suppose this is a triangular plate of total mass m. We have to find the moment of inertia about this. I will prove that it is mh square by 6. This whole plate can be divided into two right angled triangles. Mass of this is m1, mass of this is m2, total mass is m1 plus m2. This I will be contribution of this and contribution of this. Contribution of this will be m1 into h square by 6, already proved for a right angled plate. Similarly m2 h square by 6, and so simply you can see it is m1 plus m2 h square by 6, which is total mass mh square by 6. So for any triangular plate, the moment of inertia about an edge will be mh square by 6. The same can be done here also. For this plate also, if the mass is m, the moment of inertia for this plate of mass m will also be mh square by 6. Now we can use this concept of moment of inertia of a triangular plate for a rectangle. Moment of inertia of a rectangle about a diagonal. So I have a rectangular plate of length L and B. I want to find the moment of inertia about this diagonal. This is what we need to find. Now suppose the mass of this total plate is m, and this diagonal divides it into two triangles of mass m by 2h. For this triangle, the height is suppose h, mass is m by 2, and therefore I can write the moment of inertia for this plate as m by 2 h square by 6 about this edge. And for this entire rectangle, it will be twice of the moment of inertia of each plate. So I is twice of m by 2 into h square by 6. This 2 will cancel this 2, and therefore it will be left with mh square by 6. So again, what I am telling you is the moment of inertia of a rectangle will also be mh square by 6 about a diagonal, where h is this height. Now let us find this height h. To find h, what I do, I find the area of this triangle. That will be half of the area of rectangle. So area of this triangle will be half L into B. Area of a triangle can also be written as half base into height. Now if this is L, this is B, then this will be square root of L square plus B square. So area of the triangle is half of that of a rectangle, half of L of B, half of L into B. That can also be written as half base into height. So from this I obtain the value of h as L into B by root L square plus B square. We can substitute this h over here to obtain the moment of inertia about a diagonal as m L square B square by 6 times of L square plus B square. Now just for curiosity, we can check that L is equal to B if we take, then this becomes m L square into L square by 6 times of twice of L square, and that will come out as m L square by 12, which we derived for a square also. That is just to cross check whether we have calculated it correct or not. So in this part of the lecture, I demonstrated how to find the moment of inertia of a square plate, cube and triangle. Up till now in this course, we have learnt about the basics of moment of inertia. We have done theorems on moment of inertia, and we have derived the moment of inertia of certain basic shapes like a thin bar, and then a rectangular plate, square plate, triangular plate, cube, cuboid, etc. Now we will use our knowledge of moment of inertia to derive results for rings, cylinders, disc, solid sphere, hollow sphere, etc. So let me start with the uniform ring. So I have a uniform ring. The mass of this ring is m and the radius of this ring is r, and I want to find the moment of inertia about an axis which is perpendicular to the plane and passing through the center. Now we know that the moment of inertia, the basic for a continuous mass distribution is the moment of inertia is integration of dm r square. So what I do is I divide this entire ring into different elements of mass dm each. So consider one such element of mass dm. This dm is situated at a distance r. In fact, every dm on the periphery of this ring will be situated at a distance r. So this integration is quite easy. This dm r square, this r square can be taken common because it is same for all the elements, and therefore we are left with r square integration dm, which is simply mr square. So in case of a uniform ring, the moment of inertia about this axis which is passing through the center and perpendicular to the plane, the moment of inertia is mr square. Now we will talk about the moment of inertia about a diameter. So consider two diameters, one is this and the other is this. In this diagram, one of the diameters is this and the other diameter is this. So if this is one of the diameter and this is the other diameter, which are mutually perpendicular to each other, I can call this as x-axis, this as y-axis. These two lie in the plane of the ring, and this is the z-axis which is perpendicular to the plane of the ring. Now by perpendicular axis theorem, ix plus iy is equal to iz. So ix is id, iy is also id, and iz is I naught, which is mr square. So by perpendicular axis theorem, we can say that id plus id is I naught. By symmetry, all diameters are same, therefore moment of inertia about this or this will be same as id. So I can write ix plus iy as iz, ix and iy both are id, and iz is I naught, which is this. So we get 2 id is equal to I naught, or id as half of I naught. Therefore id must be mr square by 2. So moment of inertia of the ring about a diameter is mr square by 2. Now let's talk about a uniform disk. This is a disk. This disk, basically this entire part is filled now with mass, and this disk has moment of inertia I, which is to be calculated, and the axis is this. What we do is we divide the entire disk into very small rings. So in this diagram, if I show you, what I have done is I have divided this ring. I have drawn a large number of circles on the disk. So basically I have divided the disk into rings. Consider this ring whose radius is r and the thickness is dr. So consider a differential ring of radius r and thickness dr. Let the moment of inertia of this ring be di. Then for the entire disk, moment of inertia will be summation of di. So let's talk about this ring. For this ring, di is dm r square. We know that for a ring, the moment of inertia about this axis is simply dm into r square, where dm is the mass of the ring. This ring is basically a very thin cylinder of height t. Suppose the height of cylinder is t. Then the volume of this disk can be calculated as dA into t, where dA is the surface area of the flat part. This is the top view of this ring. This shaded part has area dA, which will be calculated using simple calculus. We know that area of a circle is pi r square. Area of this circle is pi r square, and if we increase the radius of that circle, the area increases. The increase in area dA can be calculated using calculus. dA can be written as 2 pi r dr. So dA will be 2 pi r dr. Now this area is 2 pi r dr. If I multiply that by this thickness t, I will obtain the volume. I write this as dV as dA into t, where dA is the surface area of the flat part. Now the volume of this differential ring is 2 pi r dr, area of the flat part into t. Now we can equate the density for the entire disk. For the entire disk, density is total mass of the disk divided by volume of the disk. Volume of the disk is pi r square t, total area into thickness. And for that ring, the volume is dm upon the volume dV, which is flat part area 2 pi r dr into t. This can be rearranged to obtain the value of dm, which is m by pi r square into 2 pi r dr. You can remember this by simply saying that the mass of the ring is mass per unit area of the entire disk into area of the flat part of the ring. Now, as suggested earlier, the moment of inertia will be summation of di, and the contribution of that ring is dm r square. Now we put the value of dm, which is calculated above, into this. This dm is m by pi r square into 2 pi r dr into r square. So in this integration, m comes out, this 2 comes out common, r square comes out common. We will be left with r cube dr integration, and the range will be 0 to r because the final radius of the whole disk is capital R. So the circles which I drew, they will have radii ranging from 0 to capital R. So 2m by r square is common. Now r cube dr integration will be r raised to power 4 divided by 4. That is a very simple formula. Integration x raised to power n dx is x raised to power n plus 1 upon n plus 1. So this is r raised to power 4 by 4. And if I put capital R in this, I get r raised to power 4 by 4. And I put 0 in this, I get 0. So finally I am left with I is equal to 2m by r square into r raised to power 4 by 4. And that is m r square by 2. So the moment of inertia of the disk about this axis is m r square by 2. Now we can extend this information to cylinders. We derived that for a ring, the moment of inertia about this axis is m r square by 2. Similarly, for a cylinder, the moment of inertia about this axis will also be m r square. For a ring, the moment of inertia about this axis is m r square. Therefore, a cylinder also it is m r square by m r square. The idea is the moment of inertia will not depend on this dimension. As suggested earlier, the geometrical dimension parallel to the axis will not affect it. Similarly, the idea of a disk can be extended to a solid cylinder. For this disk, the moment of inertia about this axis is m r square by 2. Therefore, for a solid cylinder, the moment of inertia about this axis will be m r square by 2. Also, similar to the calculation for a ring, we can show that the moment of inertia of a disk about a diameter is half of I naught. For this disk, this ID and this ID, they will add up to I naught. So I can write 2ID as I naught, and therefore ID is half of I naught. I naught for a disk is m r square by 2, and therefore diametric axis the moment of inertia of a ring, it came out to be mr square by 2, and for a disk it will come out to be mr square by 4. So that is about a ring and a disk. Let's move to the moment of inertia of a hollow sphere. So here we will derive the moment of inertia of a hollow sphere. So consider a hollow sphere of mass m and radius r. We assume that the center of the sphere is origin. We will find the moment of inertia about a diameter. Diameter is any line passing through the center. So this axis, x-axis will also be a diameter, y-axis will also be diameter, and z-axis will also be a diameter. We want to find the moment of inertia of diameter, which can be either x-axis, y-axis or z-axis. All three are going to be equal. Now this is a hollow sphere. If I choose any dm on it and I assume that the coordinates of that point are x, y, z, then the distance of this x, y, z from 0, 0 is r. Therefore I can write x square plus y square plus z square is equal to r square, where r is the radius. Now if I calculate the moment of inertia about x-axis, then I have to take the contribution of this dm and then I have to summate it. For this dm, the coordinates are x, y, z. This is the x-axis. If I drop a perpendicular from x, y, z to x-axis, the coordinates of that point will be x, 0, 0. On x-axis, y and z will reduce to 0. So the coordinate of this point will be x, 0, 0. By distance formula, this distance will be under root of y square plus z square. So the moment of inertia about x-axis will be dm into r square, where r is to be taken as root y square plus z square. So the moment of inertia about x-axis will be dm into y square plus z square integration. Similarly, I can write the moment of inertia about y-axis. It will be dm into x square plus z square. And about z-axis, it is integration dm into x square plus y square. Now the moment of inertia of all these three axes are equal, and let us say it is I, which is the moment of inertia about a diameter. So I can write I as Ix plus Iy plus Iz by 3. Since all three are equal, if we put all three as I, this becomes I. Now Ix is dm x square plus y square, Iy is dm y square plus z square, Iz is dm x square plus z square. If I add these two, so I will have twice of x square, 2 times x square, 2 times y square, and 2 times z square. So it will be dm into x square plus y square plus z square with 2 common. But x square plus y square plus z square is r square. So that makes the situation very simple. Now this r square is a constant value. It comes out of integration, and summation of dm will be only m. So the answer is 2 by 3 mr square. So you can see, by making use of symmetry, we can find the moment of inertia of a hollow sphere without involving any complex integration. So moment of inertia of a hollow sphere about a diameter is 2 by 3 mr square. Now let's talk about the moment of inertia of a solid sphere. So consider a solid sphere of mass m and radius r. The derivation is like that of a disk. We can divide this solid sphere into a large number of hollow spheres. If the volume of the complete sphere is 4 by 3 pi r cube, then for thin sphere of radius r and thickness dr, we can write the volume by differentiating this. So dv will be 4 by 3 pi. When I differentiate r cube, I get 3 r square dr. This 3 cancels out. So dv is 4 pi r square dr. So volume of this shell is dv, which is 4 pi r square dr. Now I can find the mass as density into volume, where rho is the density. Greek alphabet rho I have used to represent density, which will be total mass of the sphere divided by total volume of the sphere. So now the moment of inertia of that hollow sphere of radius r, thickness dr, we have already calculated as 2 by 3 into mass of the hollow sphere into square of the radius. So di will be 2 by 3 dm r square. dm is mass is density into volume, so it is rho dv. Rho I have already calculated as 4 pi, dv I have calculated as 4 pi r square dr into this r square. So what I get is di is equal to 2 into 4 is 8 by 3 rho, this pi is here, then r square into r square is r raised to power 4 into dr. So the total moment of inertia will be integration of this. In this integration, 8 by 3 rho pi is a constant. It's only r raised to power 4 dr. And the integration of r raised to power 4 dr will be r raised to power 5 by 5. Again, the same formula, integration x raised to power n dx is x raised to power n plus 1 upon n plus 1. So I get this as 8 by 3 rho pi r raised to power 5 by 15. Now I put the value of rho as m upon 4 by 3 pi r cube, that is 3m upon 4 pi r cube. This 3 I have moved to the numerator. So rho is 3m by 4 pi r cube. So this rho I replace as 3m upon 4 pi r cube. So 8 by 15 into 3m by 4 pi r cube into pi r raised to power 5. Pi cancels out, this 3 and 15 they cancel out, 5 will be left, this 4 and 8 they will cancel out, 2 will be left. So we will be left with 2 by 5 m r square. So the moment of inertia of a solid sphere about a diameter is 2 by 5 m r square. Up till now we have discussed the basics of moment of inertia. We have read the formula for a discrete particle system, for a continuous mass distribution, and we derived the moment of inertia for various objects like bar, rectangular plate, box, square plate, ring, disc, cylinder, etc. Now in this part of the lecture I will give you idea about radius of gyration, and also we will solve few skill based problems to understand how to find the moment of inertia of some other shapes. So let's start. So first we will talk about the radius of gyration. So let us understand what is radius of gyration. Suppose we have any object and the mass of that object is m. If about any certain axis we calculate the moment of inertia, suppose I, and I am writing I as mk square, where m is the mass, then k is called the radius of gyration. So if you write moment of inertia, whatever is the moment of inertia about that given axis, if you compare it with the equation I is equal to mk square, then k is called the radius of gyration. For example, suppose we have a ring, and for this ring this is the axis which passes through its center perpendicular to the plane. We know that the moment of inertia of the ring about this axis is mr square. So if I compare this I with mk square, I have mk square is equal to mr square, and therefore k is r. So I say that radius of gyration of the ring for this particular axis is equal to the radius of the ring. Let's think about a disk. Suppose we have a disk and this is the axis passing through center and perpendicular to its plane. We know that the moment of inertia for this axis is m r square by 2, where m is the mass and r is the radius of the disk. Now if I write I as mk square and I compare them, I will cancel m from both sides. This will be k square is equal to r square by 2. If I take the square root, I get k is equal to r by root 2. So the moment of inertia the radius of gyration of the disk about this axis is r upon root 2, where r is the radius. We can also have the radius of gyration for a bar. Suppose we have a thin bar of mass m, length L, and suppose this is the axis passing through the center and perpendicular to its plane. In the previous lectures we have derived that the moment of inertia is ml square by 12. Again, putting I as mk square is equal to ml square by 12, I obtain k as L by root 12. So we say that the radius of gyration of this bar about this axis is L by root 12. So that is about radius of gyration. You will be given radius of gyration in some questions, then you can write the moment of inertia as mk square, or in some other questions you will be supposed to calculate the radius of gyration about a given axis. So this is the process. Now let's talk about some problems on the calculation of moment of inertia. I am writing an example to give you the idea how to use the skills. We have a question: calculate the moment of inertia of a half ring about a diameter joining the endpoints. We have a half ring like this. These are the two endpoints, and this is the axis which is a diameter joining the endpoint. We have to calculate the moment of inertia about this, which is I1. Then a diameter dividing it into 2 quarters. That means I want to calculate the moment of inertia about this diameter, which will divide it into 2 quarters. We call it as I2. Then third, the moment of inertia about an axis shown in the figure.
like this. So this is passing through the center and it makes an angle theta with this line. And finally an axis perpendicular to the plane and passing through midpoint C. So the I4 is the moment of inertia about an axis which is passing through point C and perpendicular to the plane of the ring. So we will calculate them one by one. Let us see how to calculate it. First I will talk about 1 and 2. So we will be talking about this ring. This is a half ring of mass m. I want to find the moment of inertia about this, which is I1, the moment of inertia about this, which is I2. Now you see I have drawn another ring, red colored ring, another half ring. This is one half ring. I place another half ring like this so that I obtain a complete ring of mass 2m. Now the moment of inertia of this half ring about this axis and this half ring about this axis, they are going to be same. So both of them will be equal. That means the moment of inertia of this complete ring about this axis will be I1 plus I1 dash, where I1 dash itself is equal to I1. I1 is the moment of inertia due to this. I1 dash is the moment of inertia due to this. Both of them are equal. And the moment of inertia of the complete ring about this axis will be I1 plus I1 dash. Now we know that for a complete ring, the moment of inertia about a diameter is mr square by 2. Now be careful to note that the mass of this ring is 2m. So mass should be taken as 2m. That is why we are writing 2 in the red color to make it important. So the moment of inertia of this whole ring about this diameter will be 2m, the mass of the ring, into r square by 2. And since I1 and I1 dash are equal, this is 2I1 is equal to 2mr square by 2. That means I1 is mr square by 2. This 2 and 2 will cancel out. We will be left with I1 is equal to mr square by 2. So moment of inertia of this about this is mr square by 2. The same discussion holds good for this axis also. For this axis, the contribution to this part and due to this part, they will be equal. The moment of inertia of this half ring about this axis is I2 and the contribution due to this is I2 dash. Both are equal and the sum of them will be the moment of inertia of this whole ring about this axis, which is obviously a diameter. And for a diameter, moment of inertia of the whole ring will be 2m, the total mass of the ring, into r square by 2. So I get 2I2 is equal to 2mr square by 2. Solving, we will get I2 is equal to mr square by 2. So for this ring, moment of inertia about this is mr square by 2 and about this axis is also mr square by 2. That is the answer to the first and second part. Now we talk about the third part. This is the ring, this part, and this is the axis given to us. We want to find the moment of inertia. We have a simple trick over here. If you see this much part of the ring, if I remove this part and place it here, the moment of inertia will not be affected. See, moment of inertia depends on the mass and the distance of the mass from the axis of rotation. All these particles I have placed here. This particle shifted to this position, this particle shifted to this position, so that the distance of all these particles from this axis does not change when I shift over here. That means if I shift this part to this part, moment of inertia will not change. And if I shift this part to this part, then this becomes a half ring and this is the diameter joining the endpoints. And we have already calculated in the first part the moment of inertia of this axis is mr square by 2. So that means the moment of inertia of about this axis is mr square by 2. Now the fourth part. This involves some calculation. In the fourth part, we are given this half ring and there is a point C which is the midpoint of this half ring, and I have an axis passing through this point and perpendicular to the plane of the ring. And about that the moment of inertia is suppose I4. To obtain I4, I will use parallel axis theorem. I suppose that here is the center of mass. You need to have this information priorly. The center of mass of half ring is at a distance 2r by pi from center. That means this distance is known to be 2r by pi. This calculation has been done in the chapter of center of mass. So I presume that you know this result, or you may note this down in the notebook. Now for this ring, I have to find I4. I suppose ICM is here at a distance x. This distance I know 2r by pi, and this hole is capital R. So I can write x as r minus RCM, where RCM is 2r by pi. Now to obtain I4, first I will find ICM and then I will find I4. To find ICM, I will first find I0. I0 is the moment of inertia about the axis passing through center and perpendicular to the plane. To find I0, I use the similar trick as used in the previous part. This is the half ring. I take another half ring. This will have I0. This will also have moment of inertia I0. So the moment of inertia of this whole ring about this axis will be 2I0. And we know that the moment of inertia of a complete ring about this axis is mass into radius square. Mass is 2m into r square, and therefore I get I0 as mr square. So the moment of inertia of the ring about this axis is mr square. So the moment of inertia of this whole ring about this axis will be 2I0. And we know that the moment of inertia of a complete ring about this axis is mass into radius square. Mass is 2m into r square, and therefore I get I0 as mr square. So the moment of inertia of the ring about this axis is mr square. Now I can write parallel axis theorem, which is that I parallel is equal to ICM plus MD square. This is I parallel, which is I0. This is ICM, which I don't know. I have written ICM plus M into the distance between them square, that is MRCM square. Similarly, for I4 and ICM also I can relate. I4 is equal to ICM plus MX square, where x is r minus 2r by pi. Now I subtract these two equations. I obtain I4 minus I0. When I subtract ICM will cancel out. This will be mx square minus mRCM square. Out of this I can take m common. It will be x square minus RCM square, which is x minus RCM into x plus RCM. The value of I0 I have obtained mr square, so I put it over here. So I get I4 is equal to mr square plus m into x minus RCM into x plus RCM. Now if I put the value of x, which is r minus 2r by pi, I will get the final answer like this. I4 is equal to mr square plus m into r minus 4r by pi. This is this expression x minus RCM. It becomes r minus 4r by pi. And this expression x plus RCM, this becomes r. So this is the final answer for I4. Let's take another problem. I want to find the moment of inertia of a disk about a tangent. Suppose the mass is m and radius r. So this is a disk and I want to find the moment of inertia about a tangent. For that matter, I will use parallel axis theorem, and first I will find the moment of inertia about an axis through center of mass like this, which is obviously a diameter. Now we know that I0, the moment of inertia about the center perpendicular to the plane, is mr square by 2. It has been derived earlier. Now if this is ID, I know that ID will be I0 by 2. This we have used by perpendicular axis theorem. Earlier we have derived. So ID is mr square by 4. Now by parallel axis theorem, I is equal to ID plus MD square. So I will be equal to ID plus MD square. That is mr square by 4 plus mr square, and it is 5 by 4 mr square. Now let's take another good example. Here I want to find the moment of inertia of an annular disk. This is an annular disk whose inner radius is r1, outer radius is r2, mass is m. We want to find the moment of inertia about an axis through center perpendicular to the plane. This annular disk can be thought to be derived by taking out a complete disk of radius r2 and removing a part of radius r1 from it. So I take a complete disk, I remove a part r1 from it, so I obtain this. Let us say mass of this is m2, mass of this is m1, and mass of this is m. So moment of inertia of this complete disk about this axis, which is mr square by 2, m2 r2 square by 2, minus the moment of inertia of this m1 r square by 2 will give me the desired result. So to find I, all I need is to substitute the values of m2 and m1. Now how to find m2 and m1? We can compare the mass per unit area. The mass per unit area for entire thing remains the same. So for this disk it is m2 by pi r2 square. For the second disk, it is m1 by pi r1 square. For the annular disk, it is m by pi. Obviously, the area is pi r2 square minus r1 square. From this, I obtain the value of m2 and m1. m2 will be m r2 square by r2 square minus r1 square. Similarly, m1 I obtain. Now, moment of inertia, as I derived earlier in the previous page, it is m2 r2 square by 2 minus m1 r square by 2. m2 and m1 we replace by these two values to obtain this result. Now from this result we can take m by 2 r2 square minus r1 square common. We will be left with r2 raised to power 4 minus r1 raised to power 4. I can replace this by a square minus b square as a minus b into a plus b, and the final answer that will be left with me is m into r2 square plus r1 square by 2. So that is all about the course on the moment of inertia. I have tried best to give you the idea how to evaluate the moment of inertia without integration and how to use the theorems on moment of inertia. I suggest that you strongly practice all these questions in your notebook to develop these skills. I'll be back with another course.